Our next speaker, Dr. Edgar Solomonik, is returning to us from ETH, and he'll be telling us about his Cyclops multidimensional tensor framework, which is based on some ideas of his own and a little bit of inspiration from Charm++.
Thanks, sir. Okay, well, it's great to be back. I think I was last at a Charm++ workshop presenting 6 years ago, and I look forward to being at University of Illinois in the fall. I wanted to start by a little bit of motivation of kind of where Cyclops tensor framework lays with respect to existing parallel languages for multidimensional arrays, as well as kind of more general frameworks that support distributed arrays. And on the other side, numerical libraries that support parallel computations. So for example, there is hierarchically tiled arrays, and Charm++ has multi-phase shared arrays, and the Charm++ multidimensional chare arrays themselves allow one to write multidimensional array codes and facilitate that. There's also global arrays, UPC, Titanium, and high-performance Fortran, which I think all have various level of support for multidimensional array computations. On the other side, there is the numerical methods frameworks, which in particular work for matrices and vectors. And they provide various types of methods that you can use to various degrees. Scale-It-Back provides density algebra routines, as does Elemental and G-Plasma. Petsy and Trulinos, I think, primarily focus on sparse iterative methods, but also have primal support for matrices. So these are kind of two very different ends of trying to approach some of the same problems. I think many applications have experimented with using both types of frameworks to implement certain iterative solvers and applications. The more general frameworks that we have on the left typically allow the user to define an arbitrary distribution and allow for transformations and scheduling, but they only have usually somewhat limited support with respect to the scope of operations. While the numerical methods libraries provide very powerful methods, but have performance that depends on the implementation of each particular method and don't allow many transformations of the data layouts. So in one case, we have some limited API for expressing array computations and data transformations, but not a lot of power in terms of the number of operations that we can execute without implementing our own functionality. And in another case, we have this broad set of functions for different solvers, for different dense matrix factorizations that are very powerful, but may not necessarily perform well and don't necessarily allow for general application development and are hard to tweak for any particular method. So once we then think of even higher dimensional arrays, so going from just matrices to tensors, support within, I think, many of the array languages becomes more rudimentary. You're more likely to encounter bugs, and there's less features that are primarily available. While for the matrix libraries that we have, usually there is essentially no support for higher order tensors. You have to do the work yourself if you want to work with a higher order data set, to fold it into a matrix representation and operate on it. And some methods like tensor factorizations, there's just no distributed memory libraries for. So kind of the goal of this talk, and I'll be introducing Cyclops tensor framework as an approach that tries to, in a way, get the best of both worlds. To have a limited API that at the same time allows for rapid and efficient implementation of various numerical methods with tensors, so with higher dimensional matrices and higher dimensional arrays. The particular primitive that CTF was from the start designed to leverage are tensor contractions. And so a contraction involves two tensors that, and here I use this array index notation, so these are not matrices, they're higher dimensional objects. So one might be of order s plus t, this is the result, and this is order s plus v contracted with order v plus t over v indices. But in general, these v indices that you contract over can appear in as any subset of these indices. And so this type of tensor contraction primitive generalizes a lot of the very, very basic matrix BLAS operations, basic linear algebra subroutines, including the vector inner product, matrix multiplication, matrix vector multiplication, and the vector outer product. and going towards higher order objects, the tensor times matrix product, where you have one operand is some higher order tensor, and the other is a matrix, and you contract over one index. This particular primitive is the foundation of many tensor factorization algorithms, which decompose a tensor into a multilinear product of either lower order or lower rank tensors, and is quite popular in a variety of applications. So in particular, the alternating least squares algorithm is based on this TTM, tensor times matrix product. But there are many other applications for tensor computations for tensors of order higher than 2, including higher order numerical schemes. Also within computer vision and graphics, you typically have data sets that correspond to many images over time, or many images over time from many angles, which are naturally represented as tensors, and much of the analysis is simplified when working in that form. One particular application that is extremely popular right now are the convolutional networks in deep learning. There you often have, again, these kind of image and video data sets, which are correspond to order 3 tensors, and you do partial convolutions along essentially subsets of them to map to new 3-dimensional tensors or sets of 3-dimensional tensors. And these are actually often done with matrix multiplication, despite the fact that that's not really being the asymptotically optimal algorithm. So in fact, they are currently being done with tensor contractions. Okay. There's also a lot of applications for solvers for the Mighty Schrödinger equation, which leverage tensors, because there you have an equation that really has this exponential scaling, and it really requires consideration of higher order moments. Within the physics community, and especially solid-state physics, one of the most popular methods currently is the density matrix renormalization group, which expresses systems as essentially lattices, where at each lattice site you have a tensor, and overall you have a multilinear equation of tensors representing your system. One application that I will focus on was the application driver for the development of Cyclops tensor framework, in a similar way as MD and OpenAtom were some of the applications driving the development of Chum++, is the couple cluster set of applications. And one thing that really attracted me to this set of methods is the, I think, richness numerically that they have, and also, I think, the gap that one can still try to exploit with respect to making them faster. They typically have polynomial order scaling that is quite high and involve evaluating a large set of tensor contractions. So a little bit more about that. What electronic structure methods do is try to solve the many-body time-independent, which means just static, Schrödinger equation, which allows you to calculate the energy of an electronic system to high accuracy, and subsequently to model things like chemical reactions and basic properties of materials. So the couple cluster methods are very kind of higher order accurate methods that try to get you really a lot of, let's say, digits with respect to your ground state energy and further calculations. And there are 3 common types. The most common is CCSD, CCSD-T, and CCSD-TQ. And these involve CCSD singles and doubles, T triples, Q quadruples. What this means is an excitation of either 1, 2, or 3, or 4 sets of electrons to new states. And essentially, each one of these methods, as you go to higher and higher order, considers the interaction of larger and larger sets of electrons taking over a larger and larger set of orbitals, which you can think of as basis functions. So for each one of these methods, you essentially have a tensor that corresponds to having modes for each set of electrons. So either 1 electron, 2 electrons, or 3 electrons. Those are 2, 3, 4 of the modes of this tensor T, plus as many modes for the basis functions. So the order 4 tensor that you're solving for in the CCSD method has 4 modes, 2 of them corresponding to electrons, and 2 of them corresponding to basis functions. So comparing this, for instance, to calculating all of the forces in molecular dynamics, there you have a tensor, a matrix, whose modes correspond to particles and particles. So you can essentially then derive equations that solve for this tensor T and obtain an energy that's consistent with respect to a derivation of the mean field Hamiltonian, which itself can be represented as a 1 electron and 2 electron interactions, a matrix, and a 4th order tensor. And what you end up with when you essentially plug the ansatz motivated by the couple cluster into the Schrodinger equation is this huge set of terms which essentially correspond to all the possible transitions of electrons towards the higher order states. And some of the equations start to look like multilinear products of these tensors. So this is T times F contracted over one mode, and this is T times V times T contracted over 4 modes. These are then factorized into bilinear products of tensors, and you essentially get a lot of tensor contractions that can all be reduced to matrix multiplications, but require the reordering of the tensor modes in various ways for each multiplication. Within these equations, you also almost always have a lot of symmetry in the tensor representation. So the T-tensor is anti-symmetric with respect to interchange of these two modes or those two modes, which means that you can, anti-symmetric means symmetric with an interchange of sign. So you can represent the data storage and also lower the contraction cost by factors proportional to the amount of symmetry in the tensors. So, and this grows essentially exponentially with the number of modes, number of dimensions. So for the T-tensor, you can use a factor of 4 fewer elements if you exploit the symmetry. So typically, software libraries are written in order to leverage this. So in terms of the number of terms that appears in CCSD, you have 45 terms that look something like that, which are the kind of different transitions. And although only 5 to 10 of them will be leading order in cost, so you have to kind of focus on computing those most efficiently, but you also have to support a large variety. And as you go to the higher order methods, you get essentially an exponentially growing number of such terms, although again, only a small subset of them will be leading order in cost. So actually just a part of the CCSD equations actually factorized into bilinear products looks like this huge set. And what I'd just like to point out is essentially you're contracting these higher order tensors in all types of different ways. So you sum over some of the indices and others, and you get these order n to the 5th or n to the 6th cost contractions if each of the modes has length n. More generally, it's number of electrons and number of orbitals, which are somewhat different. And you have to be able to execute all of those efficiently and transition between the data layouts required to execute those. However, each one of them can be just done as a matrix-matrix multiplication after reordering. At least that's one approach to doing it. But you have to be able to do the reordering quickly, and this becomes a bottleneck, especially when you're in distributed memory and you have a data movement cost associated with the reordering. So CTF was, Cyclops Tensor Framework was motivated with respect to solving such equations and more generally just supporting tensor computations. It's a distributed memory library based on MPI and also with threading provided by OpenMP and potential acceleration by CUDA. And it has a kind of simple interface that's based on Einstein summation, so avoiding the summation signs and just describing everything in indexed form, which is actually what is done in quantum chemistry. And it primarily targets tensor contractions and also tensor summations, as well as essentially arbitrary functions on tensors, as I'll show. You can also think of this as essentially functions on multidimensional arrays and ways to interact pairs of multidimensional arrays. It also was built to support symmetric packed storage, so only storing the unique part of each tensor, and it now also supports sparsity. For both of these, we achieve nice distributions via what's called a cyclic layout, which I will explain. But first, to show how the interface looks like and explain a little bit more what Einstein summation means, if we just want to do the Jacobi iterative method, which primarily consists of a multiplication of a matrix by a vector, we can do it as such. So this is the only line of C++ code that is actually CTF code, and I've just added these comments to try to explain what's going on. So the loops over I and j over these indices are implicitly inferred from this equation. The matrix vector multiplication is here. Then we have essentially a summation. We subtract from the right-hand side the output of this matrix vector multiplication, and we scale each element, so we compute pointwise product with d, all in this kind of simple notation. Then we can compute the residual simply like that. And this norm2 function is specialized to compute the norm of a vector or a matrix. So this is the Frobenius norm, actually, for any tensor. And so now to take out the commented out loops and also show the part that I skipped for Jacobi iteration, which involves subtracting out the diagonal part and the off-diagonal part. So R here will be the off diagonal, and this means, if you can imagine 4i and then 4i, so this touches only the diagonal of R. We set that to 0, and we copy the diagonal of A into this vector D, and then define a special function that allows each element to be inverted just by, again, applying that to this tensor matrix. So this type of index notation is particularly powerful once we go on to expressing higher order contractions, in particular these couple cluster methods. So this is code that appears within the Aquarius framework, which was developed by Devin Matthews. We both started working on this domain while we were interns at Argonne now 6 or 7 years ago. So he's a quantum chemist at UT Austin, and he developed this framework on top of CTF, leveraging it to do each one of the tensor contractions, and really CTF dominates the cost of his work. But here you can see that equations that involve contraction of two fourth-order tensors that would have normally required one to write 6 of nested for loops and then manually do a parallelization over some subset of the indices are now just written as one line of code, and the framework takes care of doing all the work of parallelization and scheduling automatically. So since kind of our initial effort with Aquarius, CTF has also been adopted by some of the bigger players within the higher order electronic structure community, including QChem, VASP, and Sci4. And these are, for many of these, CTF now allows essentially distributed memory capabilities with very little effort with respect to what was already there. Okay, to talk a little bit more about how CTF works, it's a little bit more about the interface, is I kind of so far have just talked about contractions and haven't actually talked about how to initially fill up the tensor with data or extract the data. We do that essentially by this type of global array-like access where but also bulk synchronously. So each processor will write some subset and read some subset of the data defined just in key value form. And the actual layout of each tensor, so its decomposition, is hidden from the user, although one can define an initial distribution and insert the data that way somewhat faster. We also allow slicing, so extracting submatrices, or more generally subtensors, blocks of the tensor via, again, a simple routine. And we can also sum those and operate on them directly. And one can also extract different subtensors onto different subsets of processes and then break up the computation into pieces. You can also extract any permutation of the tensor. So you can imagine permuting the rows and columns of the matrix and then extracting a block of that. What we call the permute function allows this to be done essentially in one line of code. And again, each processor can, or set of processes can extract a subset, and one can then work on subsets of processes on different parts of the computation. Now, to talk a little bit about the cyclic layout and why we use it, as well as to highlight the kind of difficulties in storing a symmetric matrix. So here we have this funky representation of a symmetric matrix, and this is the part that we actually want to store. So only the lower triangular part, that's the unique part of the matrix. And if we just use a very naive block layout of what the matrix originally was, then we see that one processor owns nothing, some of them own a half of a block, and one owns a full block, so we have load imbalance and difficulties with that. If you go to a block cyclic layout, which is what's used within, for instance, scale-up and many linear algebra libraries, this would mean that each processor owns a sub-block with some cyclicity factor, which here is a factor of 2 in each dimension. You still have some load imbalance that's now smaller, but processor 1 owns a lot more than processor 2. So we use a cyclic layout, which means that essentially each second processor will own every second element in each one of the dimensions. And this allows one to extract essentially a piece of the symmetric packed layout matrix that is as close as possible to the same size on each processor. And once we actually extract this piece, which is completely non-local in some sense, we again have something that looks like a local block. And in fact, the local blocks that we have on each processor look like the overall symmetric packed laid out distributed matrix. So if we had a kernel for sequentially working with such a packed layout, we can now hope to apply it to each sub-block here once we've used the cyclic layout. It's still not perfectly load balanced, So as you can see here, this processor is missing one diagonal with respect to the other processes. But this kind of diagonal is small enough, although it can be larger for higher order tensors, that we just use padding and via this ensure that every piece of the computation is of the same completely regular size. And in fact, by kind of taking this approach, we reduced a problem that used to be treated with dynamic load balancing, in fact. So NWChem, for instance, which is a kind of a different framework for computing coupled cluster methods, leverages, kind of deals with symmetry by actually extracting blocks as we had in the block layout, and then doing dynamic load balancing in order to deal with blocks that don't exist, that are symmetric or smaller, that are essentially in this upper part. And by using a specialized layout, we've essentially made this problem completely regular. Okay, so one way where I think CTF really gets close to some of the ideas that have been employed in chare++ is in its use of overdecomposition. That is assigning multiple blocks of the tensor to the same processor. And we do this for different reasons than chare++. So in chare++, this is done because the blocks essentially contain different size subsets of the computation frequently. And by overdecomposing, we can then hope to balance out the blocks, so each processor potentially owns a different amount, and the overall computation becomes load balanced. In CTF, we do it so as to decompose the tensor in any way that we want with respect to the overall virtual topology. And this allows us to essentially preserve symmetry in the layout for an arbitrary amount of given processes. So if we want to map to a 4x2 processor grid, and we're given an order 3 tensor that's symmetric in all of the modes, we would like to decompose it such that the dimensions of the decomposition match in each dimension. And this allows the cyclic layout to preserve this nice symmetry. And we can do so by breaking it up into 64 blocks and assigning all of these 8 blue blocks to this processor. And we do similar layouts for this matrix and this tensor, which are also in various symmetric packed layouts. And so we kind of have leverage over decomposition to preserve the structure of the problem, and at the same time to work with an arbitrary number of processors. So we do want to have everything be general. Okay. So to talk a little bit more about the details of this decomposition and mapping. So I guess these 2 points I've already mentioned. But the way the mapping logic works is that we try to map to all possible processor grids. And the set of processor grids is based on some starting physical topology. So on a machine like the blue gene, either P or Q, we can actually infer the topology that we're given, and we work with that torus as the basic topology, the subset of the torus that we're given. On kind of a more general network, we have some subset of nodes, and we interpret that subset as also a torus network, except with the maximal number of dimensions. So essentially factorize number of processes we're given and say that this is a torus network. Then we form all of the topologies by considering all foldings of this base topology. So given a 3x3 an order 3 torus, we'll consider all foldings into order 2 tori, into order 1 tori, and so forth. And given a factorized number of processes, we'll consider all combinations of those factors, which all form essentially different ways to decompose and map each tensor to the processor grid. And for each contraction, we then tune over all mappings, so assignments of the tensor modes to these processor grid modes. So this allows us to essentially consider all possible layouts, for instance, for matrix-matrix multiplication, and more generally, all possible layouts for tensor contraction. Maybe all possible is a step a little bit too far, but a very large amount. And especially given a nice number of processes, so a factor of 2, maybe with a few factors of 3, we actually, I think, effectively consider all layouts that are worth considering. Then for each of these mappings and for each of these decompositions, before actually going to that decomposition, we ask, okay, how much will it cost to run the contraction given this decomposition? And since everything is regular, we can essentially derive the communication costs both in terms of the memory bandwidth, so the traffic between some cache and memory, as well as the data traffic moved between processes a priori before picking the right distribution. And based on that, we can pick the best one. And we also do this using all of our processes, evaluating a different subset of the mappings. So we leverage parallelism at runtime in order to pick the best decomposition. And so when we actually have sparsity, we also try to estimate the load imbalance caused by any given decomposition. And there's also, of course, the cost of going to and from decompositions. And for that, this is also something that's part of our performance model, but it's also something that we've put quite a lot of effort into optimizing. So I already mentioned that we had these kernels for writing and reading a subset of the data to the tensor. And these essentially correspond to a sparse redistribution. And to do that, we have an all-to-all-V as well as some binning and sorting. So this is fairly expensive sequentially and is a somewhat unstructured communication pattern. But it is extremely general in the redistributions we can express. The redistribution type that we've optimized most and is also quite powerful and the one that's most used within actual execution of methods is redistribution from one mapping, so one physical topology and one assignment of tensor modes to those torus modes to a different one. And at first we would actually do this by explicitly iterating through all the elements and computing where each one needs to be sent. Recently, we actually were able to derive an analytic recurrence for any two mappings and any types of symmetric packed layout for how many elements will be sent between a pair of processes. And this thing actually is very complicated, but it is possible to do analytically, and this has saved us quite a bit of cost. Then we essentially pack subsets of the messages that correspond to the messages defined by the lowest, the dimension of the tensor that moves most slowly. Most quickly. And then try to also optimize that in more manual ways by nested loops that are template instantiated and threading. So this kernel is really complicated, and I'm skipping a lot of the details, but essentially we've put a ton of effort into making these dunce-to-dunce mappings be as fast as possible to the point that now we're essentially always dominated by the communication and the local work of actually determining where each kind of subset of the data needs to go, which is in general a fairly irregular redistribution pattern, is now low order for the most part. There's also block-to-block redistribution, so if you want to go from the same virtual decomposition, so the same number of blocks of a tensor, to a different assignment of the blocks between processor grids, we can do that more cheaply. We do that by just sending the blocks in point-to-point messages, and we don't need to iterate over the entire data set and figure out where each given piece of data goes. Okay, now to highlight the benefit of doing these searches over the topology over partitions and actually exploiting physical topologies, let me just highlight a matrix multiplication result that we've achieved in the BlueGene queue. So with respect to scale-opaque, by leveraging what's called rectangular collectives on the BlueGene, which are the fast broadcasts you can use when you use a regular subset of the processes that nicely matches the torus. These collectives essentially benefit your performance by something like 100x. They're much, much more efficient than regular binomial collectives. And by leveraging those for a rectangular matrix multiplication, meaning that the matrices aren't square, yeah, so QBox has used this matrix multiplication, going to step ahead, to do orthogonalization within density functional. Yeah, I put the slide after we talked at lunch. I wasn't actually going to do this, but yeah, so we can get a very large speed up by being a little bit smarter about the topology. But this is like an extremely basic usage of the framework in some sense, right? So this is just matrix multiplication. So yeah, that's why they use it. Right, yep. Okay. It's much more fun to implement the couple cluster methods because they're much richer in exploiting the full generality of what the framework can do. And let me first compare it to NWChem, which is a library for electronic structure methods, which for the couple cluster methods leverages a partition global address space library, the global arrays, in order to distribute the matrices and the tensors, and then just essentially reads blocks and does dynamic load balancing. So with respect to that, you can compare the blue lines, this is strong scaling, so down is good, to the orange lines for different system sizes. The orange lines are NWChem, and we achieve much, much better strong scaling And as we go to bigger problems, so kind of going across the lines, we also achieve better performance, and we are also more memory scalable. This is for CCHD method, so order 4 tensors. This is for CCHD-T, so involving also order 6 tensors. Going further, and now both of the types of lines are our own code, but for CCHD and CCHD-T, and now we just try to do weak scaling, solving the biggest problems that fit into memory and using as many nodes as possible. And kind of what we're able to show is that in terms of the flop rate that we achieve, we're near a petaflop in performance, and we're at a state of reasonable efficiency in terms of the node performance. This is on Blue Gene Q, on Mira, and on Edison, which is a Cray XC30 system at NERSC. We also actually achieve good weak scalability, and we achieve actually an even better percentage of peak. So we are over 50% of peak on 1,000 nodes on that machine. And we actually increase in efficiency because as you weak scale these problems, there's actually more work per byte. So you have kind of a smaller data set doing more computation if you look at the global scaling. Okay, maybe I'll skip the slide. This is just where the time goes, and the point is that we spend most of the time in matrix multiplication. I wanted to talk a little bit about the new capabilities in CTF, which involve being able to have tensors of arbitrary types. So essentially, if any type that is statically sized in C++ forms migratable, but we're not quite general to being able to define objects yet. But what we do is we leverage what's the notion of algebraic structures. So you can define an arbitrary type and arbitrary multiplication and addition operators, or just whatever operator you want to define. You can also then define functions, including functions that take 2 different types and map to a third. So to give a quick example, we can define a semi-ring for path computations and graphs via the following syntax, and then we could define a matrix that's sparse and symmetric hollow, meaning it's symmetric and has no diagonal, to define an undirected graph. And using this, we can implement, for instance, Bellman-Ford as just an iterative scheme involving matrix vector multiplication over the right semi-ring in kind of a trivial amount of code. We can also do kind of more general things where you can define your own type and your own special monoid, and via this implement kind of more general graph algorithms such as betweenness centrality, which can in the end also be formulated as a matrix-matrix multiplication like kernel, here done with a function that essentially takes an int in a path and outputs another path. So it's a multi-type function. So this is, I think, closely related to the graph BLAS effort, except we also have support for tensors, but it's very much in a similar spirit. And just to show some quick results of what we're able to do with respect to sparse computations, everything I showed you before was for dense tensors. For doing sparse matrix times dense matrix, we're able to exploit sparsity to lower the cost. So the solid green line, this is weak scaling, this is strong scaling, is the dense version. This is 16% sparse, and each one of the subsequent lines has a factor of 2 less sparsity, and they're just randomly distributed. But the way the cyclic layout works, the particular sparsity structure doesn't really matter. Also means we don't leverage nice sparsity structures. We get better and better performance, and especially as you weak scale, we actually get kind of better and better relative performance. Our sequential performance is bad because the MKL kernel that we use for sparse times dense is at 10% efficiency or less, which one it really shouldn't be, and I think there should be faster kernels. But by the fact that we save the amount of communication by only communicating the sparse subset of the entries, we are able to get better scaling. And finally, to show that we can at least leverage graphs for doing all prior shortest paths by path doubling, where you again can leverage a sparse times dense kernel, we are able to achieve better performance when using sparsity. Although for strong scaling, it eventually runs out and the sparsity doesn't matter so much because you're bounded by latency. Okay, so in summary, CTF is a distributed memory framework that leverages MPI, OpenMP, and CUDA. And so literally the only dependencies that CTF has are MPI, OpenMP, and the BLAS. There's support for symmetric and sparse tensors or multidimensional arrays, if you will. And I wanted to talk a little bit about similarities to C++, which include our use of overdecomposition and virtualization, our use of topology where I'm mapping of these tasks and blocks to different processors, and also the application-driven style of development, which I think has made CTF be something that's quite usable and well documented. But there are also, of course, critical differences, and I wanted to kind of highlight differences in similar-like things. So we, in a way, do runtime optimizations and runtime kind of choices of decompositions, but we are selecting a regular schedule and a regular decomposition among a subset of those, rather than trying to do dynamic load balancing between irregular decompositions. So essentially, we're migrating tasks between these regular distributions rather than using heuristics to improve them gradually. And also, a key difference between how we do virtualization and overdecomposition is that we do redistributions on a processor-to-processor basis, and general communication is managed processor-to-processor rather than task-to-task, which in general means that we have a lower synchronization cost and can go between different layouts more easily, but also means that I think in some cases we aren't as dynamic and don't have as much. I think you can also get better cache performance if you just work on a task-to-task basis. Okay, so as future work for the graph computations that I showed, we were using kind of sequential naive kernels, and we need a way to generate essentially dgem for arbitrary element-wise functions. And we also only have sparse times dense now, and not sparse times sparse. And finally, there's a lot of features one can build on top of contractions and also optimize contractions further, including considerations of optimizations that involve not just doing one contraction faster, but a set of them or a sequence of iterative contractions. Also doing convolutions of tensor dimensions, which one would want for deep learning, and doing tensor factorizations, which have many applications, among others. That's all. Thank you. They have turbo boost on?
Yeah, because you get huge amounts of performance benefit from it.
Even, I mean...
For HPC applications?
Okay. Yes. It turns out even the least sensitive application, when something like 5 or 8% faster with turbo boost on than off, and that's before you do load balancing to take advantage of faster processors. So the question...
Might counterbalance the load balancing because it probably makes the slowest processor fastest, but then... Okay.
Well, yeah. So the question I want to ask is, given that you're talking in terms of, static distributions or, distributions that are supposed to be very regular, how does that shift when you're then dealing with processors of, unequal performance?
For now, we pay for that. But, yeah, I guess so far I think they're not that unequal. And even for... I mean, currently we're decomposing even sparse tensors, which in a way that essentially is load balanced only up to randomization. So it's not that well load balanced, and you can imagine refining that. But I think you gain so much from the regularity and the ability to exploit very nice communication patterns that it's going to be difficult to try to kind of leverage more dynamic load balancing in the Triples Plus style and amortize what you're sacrificing with respect to the regularity.
It seems to me the issue of regular mapping and distributions versus irregular is a matter of strategy, is a matter of control strategy. The basic overdecomposition scheme can still be utilized, and you can, in other words, you can imagine doing this within chunkless
yes.
with some restricted, right? You can only run on powers of 2 or maybe not squared.
You have similar restrictions, yes.
Right. So that restriction aside, we should be able to. So it should be a continuum that's experimentable within chunkless plus. Is that true? I mean.
Yes. I think you could implement much of this in chunkless plus. You would be doing the redistribution and communication patterns somewhat differently, which I tried to talk about a little bit, with respect that there you really have the view taken from each char, each block, and those interact directly, while here we're able to infer the fact that the distribution is always regular, and using that make the communication patterns happen on a processor-to-processor basis.
That's inside the implementation.
Yes, yes. So you could use both approaches, but there's some trade-offs. Yeah.
I mean, is it better to express the communication from the point of view of each block or from the point of view of processor? I suppose the expression is still okay from the point of view of block, better probably.
So you have more messages, but you have a better cache locality, I think.
That's implementation, right? You express the communication that way, and then internally you can say, okay, let's aggregate them. We know the regularity, and so let's communicate it accordingly.
Well, aggregating the messages would be difficult, I think, generally, but maybe yes.
I see. Okay.
I perform any aggregation inside chars manually of messages.
What do you mean? So, I mean, here we explicitly define the communication pattern with respect to many blocks. So, for instance, we're doing redistributions between two different layouts. We'll iterate over all the data that needs to be sent to the new layout. And this is actually also one type of communication pattern that's, I think, more difficult to potentially express in char++, where you have one multidimensional char array going to another one that's completely different on a different processor grid arrangement. I'm not sure, and essentially you have each block is scattered among some subset of blocks in a new distribution. And we're able to do that by considering the processor-to-processor level of that, so aggregating the messages of these blocks that each processor owns and communicating all of that to each other processor in a minimal amount of processor-to-processor messages. So you can imagine trying to aggregate this dynamically, but it would require extra work while we do it explicitly. Okay. Does that answer the question?
On the dynamic point, I mean, usually when you do these giant tensor contraction things, the size of the matrices and other things are fixed at the beginning of the calculation. So you could probably, unless your mathematics for optimizing your workload is approximate, or the machine isn't what you think it is, you should probably be able to just do it at startup.
Yeah, you can infer all of the tensor sizes and tensor contractions when you run, essentially at runtime, at kind of the first call.
At
so
startup.
Yeah, right.
So you could optimize everything, though maybe if there's a
but
lot
there's
of
just a lot of them,
overlap,
right? So
if there's overlap and other things, then maybe you get some
we don't necessarily exploit that, but we might have, and typically do have hundreds of different contractions. So optimizing all of those immediately has value, but currently we're not spending very much time in that anyway. So doing that dynamically doesn't really cost us much, and we do need to do it at runtime. Maybe at startup and only once, but doing it for each iteration of something like CCSD for each different type of contraction within CCSD is not itself so much of an overhead because there are more types of contractions than there are iterations.
Yep.
You're using cyclic layout to do the assignment of elements to processors. Are you also using cache-aligned allocators? To avoid full sharing in those situations?
Well, we use aligned allocations, but I think those issues are decoupled because the cyclic distribution is going between processors, right? And for each processor.
You have adjacent elements being assigned to separate processors.
But they're adjacent.
Clarify what you mean by processors? Each one of you, node or core?
Processes, not threads, right? So essentially, each one has a distinct memory mapping, right? So we are. The tensor is never arranged in the contiguous layout in the global sense. It's never in some global memory, right? It's explicitly distributed from the start.
Oh, I thought we were talking about at like the CPU level, like the tensor that you would be working on, in 12 cores or whatever, so that locally it would be laid out contiguously. Whether or not it's laid out globally contiguously is another.
So here we would have 12 processes, each one of which has its own memory, so their own shared memory. So they're not reading, nearby cache lines. We just partition the overall matrix or tensor in a way that each process owns a subset of the global thing that is, but it's a contiguous in memory.
So what
You're doing a
Yes, yes. So locally for the threads, we don't actually have anything that uses cyclicity. There we'll do other partitioning schemes actually. So once we do have a tensor, so we do use threading, but in which case we have kind of a shared memory and have to worry about fault sharing, but we don't actually do cyclic partitioning among the threads. We do a different type of partitioning there.
Thank you one more time.